rich in light-colored, lighter-weight minerals, especially silicon and aluminum, and the magma that it came from was closer to the surface. On the other hand, lava cools very quickly when it hits Earth's surface, which limits how crystals grow. Extrusive rocks like basalt end up with small individual minerals and a fine-grained texture that looks much more seamless. And basalt is mafic, which means it's rich in darker, heavier minerals like compounds of magnesium and iron. Even though it formed from lava on the surface, the original magma was deep in the Earth's crust or mantle. Yet somehow, our chunk of granite made its way to the surface. Like maybe it was uplifted as the Indian plate pushed further north and as the Himalayas rose. At the surface, rocks have to deal with different temperatures and pressures than where they formed deep within the crust. Not to mention weathering and erosion, or being broken down by the Earth's atmosphere, water, and living things. Water, with its ability to dissolve practically anything, can especially alter, disintegrate, and decompose rocks. The pieces can then be picked up and deposited elsewhere. So once the extra rocks and soil are removed by weathering and erosion, our granite is exposed to a totally new surface environment. And it might seem like the granite outcrop is just sitting there doing nothing, but unseen processes are operating. Like the pressure is different out here on the surface, so the outer few centimeters of the rock might expand outward and crack. Then the loose outer layers of rock can slough off, like a snake shedding its skin, or temperature differences can also cause the rock to expand or contract. This leads to granular disintegration, or when individual mineral grains break free from a rock, which is how over thousands or millions of years, tons of little rock dust pieces accumulated around the base of this granite. So as clouds gather over the mountaintop and a steady rain begins, the little mineral grains can get washed into a stream and may eventually be dropped along the channel banks during the flood. Or they'll bounce along with the water and travel all the way to where the river empties into the sea and the grains become part of the ocean bottom. Grains like these are sediments. Centuries of monsoons and soil erosion have blanketed the floor of the Bay of Bengal in up to 20 kilometers of sediment from the Himalayas. So part of our granite boulder is actually lying on the bottom of the ocean. If we could slice into all the sediment lying on the floor of the Bay of Bengal, we'd likely see horizontal layers or strata from different times when large amounts of sediments were deposited. Over time, the pressure from the weight of the material above compacts, cements, and transforms the sediments into sedimentary rock, which still shows some of the original layers. So sedimentary rock like sandstone is made of cemented sand-sized particles of quartz and other minerals. It has very visible grains, lots of tiny little holes, and is very resistant to weathering. Other sedimentary rocks like limestone are formed when the remains of organisms like shellfish, corals, and plankton sink to the ocean floor. Coal is another one of these organic sedimentary rocks that's created when organic matter accumulates and compacts in swampy environments over millions of years. At the bottom of the ancient Tethys Sea, which disappeared about 20 million years ago, sedimentary rocks would have formed from sediments brought down by rivers. But as the Indian plate pushed northward, the gap between the Indian plate and the Eurasian plate narrowed. As the plates collided and the Himalayas formed, the sediment on the seafloor was compressed and crumpled. On top of being squished and crumpled, the Indian plate and the Eurasian plate narrowed. As the plates collided and the Himalayas formed, the sediment on the seafloor was compressed and crumpled. On top of being squished and crumpled, the rocks also have to go through intense temperature and pressure changes. All this action causes the existing rock to go through metamorphism and change into a completely new rock type. All the minerals from the original rock recrystallize without having to melt down into molten rock. The new metamorphic rocks are typically harder, more compact, and more resistant to weathering. So if any sediment from our chunk of granite got caught up as the Tethys Sea was sucked under, it would probably change into gneiss. Gneiss has alternate bands of light and dark minerals and can form from a variety of different rocks. It's also very hard and resistant to weathering and erosion. So our granite boulders started life as igneous rock. But as pieces broke off, they could have been compacted into sedimentary rock or changed into metamorphic rock. It seems like it sat there for all of time, but rocks like our chunk of granite are continuously altered over millions of years from one rock type to another as a part of the rock cycle. But the story of our granite is not the story of all rocks. There are many pathways through the cycle. Like igneous rocks could skip being sedimentary rocks and go directly to being a metamorphic rock, or even remelt and recrystallize to make new igneous rock. Whether scaling a 3,000-foot high granite monolith or kicking a pebble down the road, each piece of rock has a story that may be millions of years old, etched in the stone by processes both on the surface and deep within the earth. Next time, we'll tell the stories of another kind of shapeshifter, continents, and how plate tectonics have created the Earth we know today. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages. So we at Crash Course want to acknowledge these Indigenous and Aboriginal nations through the websites and resources they provide.